In the previous lesson, we learned how to analyze and graph exponential functions. In this lesson, our learning objective is to solve problems involving exponential growth and decay functions. So to help us understand compound interest, we have this diagram here, which is of a snowball rolling down the hill, getting bigger and bigger as you go along. This is what we call the snowball effect. Now, compound interest works in a similar fashion. Imagine this is your initial value. So when we roll our first snowball, we compound and we get a new layer added on to the previous one. And then if we compound again, we get another new layer added on to the previous one. And this continues all the way throughout. So the formula for compound interest is the following. So we have A as being the account balance after compounding. P is the principal amount. Now this is the original value or the initial investment that was made, the starting value. So you can think of it from this snowball as the first value over here. R is the annual rate of interest, and it must be in decimal form to use this formula. N is the number of times the interest rate is compounded each year. And T is the number of years we want to invest for. The number of times the interest rate is compounded each year, or the value of N, can vary depending on the keyword in the question. So we have a table of keywords here to determine the correct value of N, so we can substitute correctly into this formula here. So if we compound annually, this is once a year, semi-annually, twice a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times a year, hourly, 8,760 times a year. Now this last one may be difficult to recall, so as long as we remember that there is 24 hours in one day and 365 days in a year, we simply multiply the two together to give us 8,760. So as long as we understand these terms here and these table of keywords for the correct value of N, this formula here is quite simple to use. So please make sure you make a note of these. So in example 1, Khadija invests 300 dirhams in an account with a 6% interest rate, making no other deposits or withdrawals. So no extra money is put into the account and no money is taken out of the account. What will Khadija's account balance be after 20 years if the interest is compounded semi-annually, monthly or daily? So the first thing we'll do is we'll highlight the key bits information like so, and we'll write down the formula for compound interest. So we'll begin by looking at part A. So the initial investment is 300 dirhams. This is our principal amount. So P equals 300. 6% interest rate. We need to convert this into decimal form. So we do this by dividing by 100 to give us 0.06. So R equals 0.06. After 20 years, T equals 20. Now because we compound semi-annually, N equals 2. Now that we have these values, we can substitute them into this formula here, like so. We can compute this to give us the value 978.61, which then completes the question that after 20 years of compounding semi-annually, Khadija's account balance will be 978.61 dirhams. Now for part B, these values of P, R and T and this formula will remain the same. So if we compound monthly, this tells us N will be equal to 12. With these values, we can then simply substitute into this formula like so, and compute this to give us this value, and then we've completed part B. So 993.06 dirhams will be the account balance after 20 years of compounding monthly. So now for part C, the values of P, R and T remain the same, and obviously we have the same formula. So if we compound daily, then N equals 365. We can substitute these values into this formula here, like so, and then we can compute this to give us this here. So our final answer, after 20 years of compounding daily, Khadija's account balance has 995.94 dirhams.
Now before we continue, Please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom, where we cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. The first session is always free. So if you are interested in a free lesson, click the link in the description below. To book a lesson, you can always send us a direct message on Instagram at Mr. Mathematics. Okay, with that said, let's get back to our lesson.
Now it's your turn to answer this similar question. So it says you pause the video before I reveal the answers. So the answers are the following. So moving on to continuous compound interest. If you can recall the formula for compound interest, we'll be using these values of P, R and T from example 1 and we'll substitute them into this formula here to give us this part in this table. Now you'll notice we haven't substituted any values for n just yet. The purpose of this table is to see what happens as n increases. So if I substitute these values of n into this formula here, these are the values I get for the account balance. So notice that as n increases, the values of the account balance also increase. Now, the amount they're increasing by, if we look at them over here, you can see it's slowing down. So it appears that these values are tending towards a value closer and closer to this value here. So what happens if I increase the values of n? What would be the limit of the account value if you continuously compound? Well, we can find this limit by substituting larger and larger values for n. However, this will be quite time consuming and not quite accurate. So there's got to be a quicker and more accurate way of answering this question. And luckily for us, there is. Now, if we continuously compound, essentially we are saying n tends towards infinity. So as n tends towards infinity, we can replace this formula with this formula here. And this is the formula for continuous compound interest. Now, the proof of this formula is beyond the scope of this course. However, we do need to just understand that to answer this question, what is the limit if we compound continuously, we use this formula instead. So in example 2, we have a question which is nearly identical to example 1. However, in this question, we've compounded continuously. So we need to make sure we write the correct formula, which is this one here, for continuous compounding. Now we'll highlight the key bits of information. So we have the principal value of 300 dirhams, the interest rate, and the time t after 20 years. Now be sure for the interest rate, we write it in decimal form, not in the percentage form over here. So now we can substitute these values into this formula here, like so, and we can calculate this to give us an approximate value over here. So with continuous compounding, Khadija's account balance after 20 years will be 996.04 dirhams. Now it's your turn to answer this similar question. So it says you pause the video before I reveal the answers. So the answers are the following. Now we've seen exponential growth functions being used in investments like we just looked at in the last two examples for compound interest. However, the populations of people, animals, bacteria, and the amounts of radioactive material can also change at an exponential rate. And they can be modelled using exponential growth or decay models. So we have this formula here where n stands for the final amount, so this could be the final population size. N sub 0 is the initial quantity, so this could be the starting population. R is the exponential rate, which has to be in decimal form. And T is the time element. Now it's usually in years. However, it's more appropriate for organisms such as bacteria to have it in seconds or microseconds. And another thing to note, if R is a growth rate, then R is strictly greater than 0, so it's a positive number. If R is a decay rate, then R is strictly less than 0, so it's a negative number. Now previously, we had a continuous compound interest formula. Similarly, we also have a continuous exponential growth or decay formula. And you'll notice here that we have a natural base e. All the other terms in this formula are identical to what we have here. The only thing that has changed is the letter r has been replaced with the letter k. But they still mean the same thing. It's still the exponential rate that has to be written in decimal form. Now, we had conditions on r over here. You can see the conditions are identical for k. So if k is a growth rate, then k is strictly greater than 0, so k has to be positive. If k is a decay rate, then k is strictly less than 0, so k is negative. So in example 3a, we have this question, which is about population. Now, Mexico has a population of approximately 110 million. I'm going to highlight this. If Mexico's population continues to grow, another keyword, at the described rate, predict the population of Mexico in 10 years. So I'm going to highlight this as well. Now, the described rate in part 1 is 1.42% annually. Now, because of this word annually, I know to use this formula. Okay, so n sub 0 is equal to 110 million. This is the initial or current population size. Okay, we just have to be careful we write the correct amount of zeros. Now, r is equal to 0.0142. So all I've done is simply converted this into decimal form by dividing by 100 to give me this. You'll also notice this is a positive number. Okay, and the reason it's positive because this is a growth rate. So we have to be careful to look out for that as well. And the time t is simply 10 years, which we got from the question. Now that we have these values, we can substitute into this formula here, and that'll give us this. And then we can compute this on our calculator to give us an approximate population size of 126,656,869 after 10 years. So for part 2, we have the described rate as 1.42% continuously. So because it's continuously, we use this formula over here. Now, the initial population size is still 110 million. The exponential rate is still 0.0142. We simply replace the r with the letter k, and the time t is still 10 years. We substitute these values into this formula here, like so. And then when we compute this, it will give us an approximate value of 126,783,431. In example 3b, we have a similar question about population. So the population of a town is declining at a rate of 6%. If the current population is 12,426 people, predict the population in 5 years using each model. The first thing we do is we highlight the important bits of information, like I've done there. Now, for the first part, the population is declining at a rate of 6% annually. So this tells me this is the correct formula to use. The initial population size is 12,426 that we got from the question, and the exponential rate is negative 0.06. Now, firstly, all we've done is divided this by 100 to write it in decimal form. And because it says declining, this means it's a decay rate. So this has to be a negative number, a negative rate. And then the time t equals 5 years. Now that we have these values, we can substitute into this formula over here, like so. And then we get an approximate value of 9,119. Now for part 2, it's going to be declining at a rate of 6% continuously. Now because it's continuously, this tells me I will use this formula over here. So the initial population still is the same, 12,426. Okay, the exponential rate is still negative 0.06. Again, we've just replaced the r with the letter k, otherwise it remains the same. T is 5 years as previously. So now we substitute these values into this formula over here, like so, and when we calculate this, we get an approximate value of 9,205 for part 2. Now it's your turn to answer this similar question. So it says you pause the video before I reveal the answers. So the answers are the following.